Welcome. Thank you for joining us. We're going to give just a few minutes for folks to get tuned in and connected to make sure we can get everyone logged in. I have a couple of announcements before we get started. Just a reminder that these sessions are being recorded. They will be available for you in the Whova app in the next 2 weeks, and they will be able to be viewed for 6 months following the Congress. If you have any questions today from our speakers, we ask you to please put them directly in the chat or the Q&A to the right of your Whova window. And we kindly ask that you keep your microphones and cameras off during the presentation. It looks like we are ready to get started. So I'm going to go ahead and introduce our first speaker. Korina, I'm going to turn it over to you. Korina, it looks like you're still muted. We can see the bird. Yeah. There you go. Okay, now we can hear you.
Thank you. I'm sorry.
Yeah. Looks great.
Okay, when you say me.
Yeah, you're all set. Looks good. Thank you.
Okay. I start?
Yes, thank you.
Okay. Good afternoon, everyone. I'm going to present the preliminary results of one of my doctoral thesis chapters. The main idea is to show you the advances in creating the AFIRE database, an approach to the global knowledge to evaluate the relationship between plant traits and their flammability. We lie on a flammable planet where most terrestrial plants can burn under the right climatic conditions. However, climate change alone cannot explain current fire regime difference for wildfires. Let me, the pointer, yeah. Wildfires require the confluence of the less force factor ignitions, continuous fields, drought, and appropriate weather conditions. Climate change increases drought frequency, extending the fire season and increasing the frequency of dry years. Also, human factors, apart from those associated with climate change, modify ignition patterns and landscapes to increase the ignition probability, coinciding with extreme weather in landscape with continuous fuel beds. And the greenhouse gases generated during wildfires fuel the climate crisis that favor fire spread. In this context, fire-prone ecosystem relied on multiple factors contributing to fire generation and spread, igniting particularly plants to maintain a flame. At the individual plant scale, different trends define 3 flammability strategies observed in fire-prone ecosystem, like non-flammable, fast flammable, and hot flammable. For example, for a hot flammability strategy has fields characteristic like high standing dendrobiomas, high branching, thin leaves or branch tips, high volatile compounds, low moisture content, and dense and compact form to the architecture plant. And these strategies increase the survival or reproduction under recurrent fires, and plants in fire-prone ecosystem benefit from adhering wound. These forms represent alternative ways to live under recurrent fires. This ability of plants to burn in the presence of an ignition source is called flammability. Therefore, it is informed about the ability of a fuel to burn under the flammable climatic condition in the presence of an ignition source, being the fuel of a plant organ, a whole plant, or a plant community. The flammability can be determined through four components. Ignitability is how easily a fuel ignites. The combustibility is how intensely it burns. Sustainability is how long it burns. And consumability is how much it burns. Several flammability studies with different methodologies have been generated over time. The first tests were conducted with a small plant parts, such as leaves, small twigs, and leaf litter, using instruments such as a pyradiator, mobile furnace, calorimeter, and others. Afterwards, since 2011, burning long branches in a short flammability device, from now on, we will call it grill. As a result, the grill show more realistic flammability values, like the arrangement of leaves, branches, and the plant architecture affect the fuel connectivity and airflow through the fuel, influencing the flammability. For this reason, the purpose of this review was to identify and summarize the data from studies that evaluated the relationship between plant traits and plant flammability in laboratory experiments. For the data collection, we searched the literature to collect studies like articles, theses, books, and technical reports quantifying the plant flammability attributes. The databases associated with Web of Science, Google Scholar, and university repositories was consulted for review. The general search includes keywords like plant flammability, trait, and strategy, considering the combination and the Boolean operators for each database. For the study selection to be included in database, the studies had to meet the following criteria, including quantitative data on flammability, attributes at the species level, specify the name of the species studied, and indicate the plant park burning. I mean, the branches, the litter, or leaves, the ignition methodology, such as mobile furnace, epiradiator, grill, and others, and the measurements used to determine the flammability components, such as ignition time, maximum temperature, and others. And for the homogenization of the variable flammability names, the description of each one was taken into account within the original study to later group them according to their characteristics and units. For the taxonomic and functional plant description, the corroboration of a species name was carried out with databases such as the plant list and taxonomic names resolution service. And the search for the growth form, I mean trees, crops, climbers, and others, was made using plant trait database, set information database, and word species database. For the fire propensity was classified, taking into account the location where the study was conducted and not the distribution area of the plant. For this, we crossed the location information of each of the studies with units where the terrestrial ecoregions and biomes proposed by the World Wildlife Fund. And subsequently, these layers are crossed with the fire activity classification by Pausas y Ribeiro of 2017. Well, here we see our preliminary results into the data description. We found 651 papers related to some flammability variables. And after review, we collected around 7,000 valid observations from a total of the 191 documents chosen under the selection criteria. We can see the orange point represent the study's location where flammability traits had been evaluated in different world regions. In this graph, we can see the publication related to the flammability trait published in the last 60 years. classified according to the biome where it's located. Historically, flammability has been accessed in Mediterranean ecosystems, occasionally in temperate forest. However, since 2011, when Jauregui very great device study appears, the biomes with flammability is measured have diversified, particularly among the different types of tropical biomes. In this slide, show the fire propensity by biome according to the number of the records that each one presented. We can see how fires occur in all biomes at different levels of fire activity. And this variability is given the climate and fuel availability as drivers of fire activity. In this sense, we see how the Mediterranean ecosystem, the temperate grassland and temperate broadleaf are the most studied biomes present high fire activity. As for the species, we collected 1,310 species with taxonomic status, belonging to 156 families. The most representative is the ones we see in the graph, where Pinacea has most significant number of records. Overall, these species with the most record in the database from this family are Pinus halapensis, Pinus palustris, Pinus pinaster, and Pinus contorta. Regarding to woodiness, 82.8% of the species correspond to woody plants. And in this sense, 34% are trees, and this percentage, most of which are evergreen with 76% of the records. For the preliminary flammability data, the combustion device most represented in the database are the grill, with 26.4% of the records, and epi-radiator with 26.3% of the records. On the one hand, the grill is a novel device that improves the understanding on the plant flammability and provides a more realistic comparison of relative canopy flammability between species and methods using smaller plant components, providing better details of fire behavior. In addition, it must be built to certain specification at low cost. On the other hand, the epi-radiator prevents the inflammation process, and it is a device that does not require greater specificity in the use. The most studied flammability dimension is sustainability with 36%, followed by the ignitability with 27%. In this ordinal result, in this graph, we can see the variable studied, and the color of bars are relating to the flammability dimension. In this sense, the ignition time was the most studied variable with 20.9% of the records, probably because it is too easy to measure, and it is also provides essential data for planning and optimizing field management plan in fire risk prediction. And finally, the most used plant part for burning is the leaves with a 35.1%, because the variability of their flammability is related to the response of foliar traits to environmental variables, thus greatly influencing the fire sustainability. And branches with 27.1% followed them because it's the best describe the way fire can be spread. This compilation showed the wide biogeographical distribution of flammability studies. Most of them are located in temperate broadleaf, temperate grassland, and the Mediterranean forest. And this last had a relationship with recurrent fires by their vegetation types. Real flammability has been extensively studied. Improvement must be made in determining consistent and repeatable measurements methodologies. With these advances in methods and analysis, the links between the laboratory results will become more apparent. And these preliminary results open the space for further research on the relationship between environmental plant traits, flammability. And in this sense, it is essential to collect more data and consider biotic and ecological pressures that affect plant trait variability and species flammability. Finally, the most important result is that the fire have a global impact on ecosystems that were not previously taught by fire prone. And the advances in our compilation could help to identify gaps in the knowledge of plant flammability and will hopefully guide the development of comparable or applicable procedures in an increasingly flammable world. And the knowledge of the species level flammability is required to understand the vegetation fire dynamics. It is also crucial in the fire prevention and post-fire restoration efforts. We would like to acknowledge the work carried out by the researchers whose publishing data were used for this database, and the Fire Ecology for the scholar registration. And thanks to you for your attention.
Thank you so much, Korina. I appreciate the time. I don't see any comments or questions in the chat right now, but if anyone has questions for Korina, go ahead and drop them into the Whova chat window to the right of the screen. And in the meantime, while we wait for any questions to come in, Korina, let's have you go ahead and stop screen share, and we'll invite Jacky to go ahead and begin screen share so we can get our next presenter ready to go. Hi, Jacky. Thanks for joining us.
Hi.
All right, it looks like we have one question for you, Korina. This is from Tim Curran. Excellent presentation, Korina. What are the next steps with this amazing database? Any plans to look at a trait flammability relationship?
You heard me?
And now we can hear you. Yeah, go ahead.
Okay, the idea is to be able to finish cleaning the database. It's a lot of records, and then later submit the data article. And parallel to that, maybe to create the web page with a friendly interface, maybe to share the data, and perhaps to be able to give the option to continue adding data which follow the specification we proposed.
Great, thank you so much, Korina.
Thanks to you.
All right, well, I don't see any more questions, but if anyone does have additional questions for Korina, we'll go ahead and ask Korina to follow up afterwards with any additional questions that come her way. And let's go ahead and introduce our next speaker. Jacky, I'll pass it off to you. That looks great.
Okay, should I start?
Yes, you're all set. Go ahead.
Okay. Hello, everyone. My name is Jacky Fayad. I'm a PhD student at the University of Corsica Pascal Paoli. Today, I will present a numerical study about junction fires on slope terrain.
You may need it. There you go. There you go.
Okay. Wildfires are considered natural disasters or necessary perturbations in the life on ecosystem when they maintain the ecological equilibrium and the renewal of forests. However, this approach reaches its own limit when the wildland-urban interface is affected. In this context, wildfire modeling appears to be a promising approach in order to predict the fire behavior. Wildfire modeling objectives are to understand the physics governing the fire behavior, develop better firefighting infrastructure, estimate ecological fire effects like fuel consumptions and tree mortality. Wildfires modeling approaches are divided between empirical and semi-empirical models based on experiments in order to estimate the physical parameters, or fully physical models based on the approximations of fluid dynamics equations like the combustion degradation models, and the fully physical model to be used in this study will be FIRESTAR 3D. The theoretical approach to be used in this work is a fully physical model for wildfire simulation that account for the different physico-chemical phenomena encountered during fire. It consists of coupling a fluid mechanics problem consisting of a turbulent atmospheric boundary layer characterized by quite different length scale, like the fuel height scale, the smallest turbulent structure, the flame diffusion thickness. This problem is coupled with a solid fuel problem where we describe different processes like dehydration, pyrolysis, combustion of the solid phase. The presence of soot and hot gases, radiation and convection introduces an important length scale, which is the radiation extinction length. Moving to the mesh governed in the numerical computational domain, the fluid phase mesh must be refined near the ground, and it must be smaller than the radiation extinction length, equal to 4 over the product of the surface area to volume ratio and the fuel volume fraction. Concerning the solid phase mesh, a minimum number of cells must be required within the fuel bed, and in this mesh, there are solved different equations like the continuity equation, momentum, energy, turbulence, and so on. On the solid fuel phase mesh are solved all the equations describing the degradation of the vegetation. Now moving to the junction fires. What are junction fires? They are an idealization of two merging line fires that often leads to dangerous and very high fire intensity. So in this work, we account to study numerically junction fires on slope terrain using the fully physical model FIRESTAR 3D. The first objective of this work is to study the slope effect on fire behavior in order to determine the threshold value of slope beyond which there is a change in the fire behavior characteristic. The second objective is to study the effect of junction angles variation on the fire behavior in order to determine the relationship between the speed of the junction point, which is the rate of spread, and the junction angle variation. Finally, we will study the case where we have a rotation between the junction axis and the main slope direction axis, and we will determine the effect of this rotation on the junction point speed and trajectory. Now we'll start by the slope effect on fire behavior. Concerning the numerical simulations, they were carried out using periodic boundary conditions on the two lateral sides of the computational domain. This computational domain is divided into three main zones, where the grassland vegetation zone has a length of 60 meters and a height of 70 centimeters. All the physical parameters describing the grassland vegetation, like the fuel volume fraction, the surface area to volume ratio, the dry material density, are listed in this table. Concerning the fuel moisture content, it is equal to 5% in this study. The burner is activated instantaneously along the entire fire line, where the fire is set on by injecting CO gas from the bottom boundary of the computational domain at a temperature of 1600 Kelvin, and the burner is kept on for 10 seconds. Numerical simulations were carried out for different slope angle values, starting from 10 degrees to 45 degrees. Moving to the results, they show a nonlinear relationship between the rate of spread and the slope angle variation, where the ROS increases with higher slope angle values. Also, we notice that the fire becomes subjected to a sharp acceleration starting from 25 degrees, which indicates that there exists a threshold value of slope beyond which there is a noticeable change in the fire behavior characteristics. Results also show fire behavior, flame structure, and width of the flaming zone with respect to different slope angle values, 25 degrees and 40 degrees. Here we notice that the flame inclination to the ground is more important with higher slope angle value. This is due to the existence of a buoyancy force that acts in the opposite direction of the gravitational acceleration component acting in the main slope direction. So this reinforces the Coanda effect. So the hot gases becomes rapidly pushed along the fuel bed, preheating the vegetation located ahead of the fire front, which causes the acceleration of the fire front speed. Now we will move to the junction fires on slope terrain study, starting by the first case where the junction axis is aligned with the main slope direction. Numerical simulations were carried out using this computational domain where the fire lines have V-shape in order to present the junction fires. Physical parameters are as previous because we used the same grassland vegetation, and the numerical simulations were carried out for two different slope angle values, 25 degrees and 45 degrees, and for a set of junction angle from 20 degrees to 180 degrees. Results show that for a high slope angle value of 45 degrees, there is an almost linear relationship between the rate of spread and the junction angle variation, where the ROS decreases with higher junction angle values. However, for a small slope angle of 25 degrees, this linear relationship is only present for small junction angles, where higher junction angles starting from 120 degrees have no effect on the rate of spread, which means that the relationship between ROS and junction angle variation strongly depends on the slope angle value. Here we will show temperature fields and streamlines obtained in the horizontal plane z equal 1.4 meter for a slope angle of 25 degrees and a junction angle of 30 degrees for different simulation times. Here we can see that there is an aspiration of the flow and concentration of this flow in the y median plane, which causes the acceleration of the junction point that moves along the y symmetry axis of the computational domain. Here we will show the distributions of the solid fuel dry material fraction along the fuel bed surface, taking the first case where the slope angle value is equal to 25 degrees. And here we will do a comparison between two junction angles. For the junction angle equal to 20 degrees, the time needed by the fire front to reach the middle of the vegetation is smaller than the time needed by the fire front to reach the same position with a higher junction angle, which indicates the effect of a small junction angle in increasing the fire's rate of spread. To shed light once again on the slope effect, we will do a comparison with a second case where we have a higher slope angle value of 45 degrees. We notice that the fire front traveled the same distance faster. And we can also notice that the charcoal fraction in black is more important with higher slope angle value, which is an indication of a larger fire front width leading to a higher acceleration. Now we will move to the second case where the junction axis is not aligned with the main slope direction. So here we have a rotation angle phi between the junction symmetry axis and the main slope direction axis. So here we have an additional acceleration gravitational force that acts in the y direction. In this study, we choose a GY positive. We take the case where we have a slope angle equal to 25 degrees, a junction angle of 30 degrees, and a rotation angle of 30 degrees. We can notice that the junction point moves along the y negative direction. This is due to the presence of the buoyancy force that acts in the opposite direction of the gravitational acceleration component acting in the y positive direction. So here we determined the effect of rotation in changing the trajectory of the junction point moving along the computational domain. Finally, we will show the effect of rotation on the junction point speed. So we do a comparison between two cases where we have two different slope angle values, 25 degrees and 45 degrees. We take also two rotation angles, 30 and 60 degrees, and a junction angle equal to 30 degrees. We notice that the presence of rotation decelerates the junction point speed. And we can notice also that this deceleration is more important when we have a small slope angle value, because the presence of a high slope angle value leads to a higher rate of spread, so the fire becomes less subjected to the perturbations of rotation. As conclusion, these numerical results of FIRE-STAR 3D show a nonlinear relationship between the rate of spread and slope variation, which is in good agreement with the previous results that account for the existence of a threshold value of slope beyond which there is a noticeable change in the fire behavior. Also, this first numerical study about junction fires shows the effect of small junction angle in increasing the rate of spread, and it also shows the effect of rotation between the junction axis and the main slope direction in changing the junction point speed and its trajectory. Thank you for your attention.
Thank you so much, Jacky. It looks like we've ended just a little bit early, so we have plenty of time for any questions. So if our audience has any questions, please go ahead and drop them in the Q&A in the Whova tab. See if anything comes in. And for any of our co-presenters, if you have any questions of Jacky, go ahead and turn your camera and mic on and go ahead and ask them directly. I don't see anything coming in yet, but Nathan, if you have a question, go ahead.
Yeah, hi, Jacky. Thanks for the
Hi.
great presentation. I'm curious to know whether you've thought at all about any sort of fieldwork or independent validation of what you've looked at so far.
Yes, actually, this was a preliminary study about the junction fires. Now, I have a colleague that study the junction fires made in laboratory experiments by Viegas. There are the experiments of Viegas and Jason Sharps, and he continued this work by doing a validation, if we can say that, of this numerical study using the data of the laboratory experiments made by Viegas and Jason Sharps. So this was preliminary results. This is the first numerical study made to study the junction fires on a slope terrain, especially.
Great. Any sense on whether what you've seen in your model lines up with the data there? Have you had a chance to do any comparisons?
Sorry, I don't understand.
I don't know if you've looked at the validation data yet, but if you have, is there any sense of how well your results would line up with what's been done in the laboratory so far?
Yes, that's why we continue to work on this. This was a 6 months, the results of 6 months working on it, and there's a continuity of this work for sure.
Fantastic. Thank you.
Thank you.
Well, thank you both. I don't see any other questions coming in, but we do invite our audience to go ahead and put any comments or questions in the chat if you want any additional information from Jacky. Otherwise, Nathan, or I'm sorry, Kristin, you're going to be up next, but we have about 5 minutes or 4 minutes, and I want to kind of keep us to schedule just so that if you have folks tuning in just for your session, they don't miss anything. But if you want to share screen, we could get set up and we could get started in just a moment. We'll just give it another moment to see if there's any other questions for either of our first two presenters. If anyone has any additional questions for Jacky or Korina, please go ahead and put them in the Whova, and we'll make sure that all of our presenters spend some time going back and looking for any conversation or questions that may have been missed. As we continue the conversation about fire behavior, our next speaker is Kristin. Kristin, your presentation looks great. Thanks for getting that all set up.
Yeah, I'll just wait a couple more minutes. I know a couple people are tuning in, so.
Perfect. Yeah, I'd hate for anyone to miss anything. I know it's a busy schedule. Lots of folks trying to catch as much as they can. Here's a new guest coming in now. Kristin, it looks like you're tuning in from the office today. So many of us are still working at home.
Right.
Nice to see that some offices are open.
It is, but the heating is broken, so it is like 78 degrees in here. So it's very hot.
No. Oh, it's overheating.
It's overheating, exactly.
Well, I suspect it's cold outside. All right, welcome to our new guests. Thank you all for tuning in. We're continuing the discussion about fire behavior. We ended our last presentation just a few minutes early, so we're just giving another minute for folks to join before Kristin kicks us off. All right, well, thank you, everyone. We are now at our starting time. So Kristin, I turn it over to you if you want to get started.
Perfect, thanks, Sam. Good afternoon, everyone. My name is Kristin Nesbit, and I am a master's student at Utah State University. And I'm coming to you today from Logan, Utah, which is the ancestral lands of the Shoshone-Bannock and Eastern Shoshone people. So today I will be presenting on some initial findings from my research this past summer of assessing fuel characteristics and fire behavior along ecological gradients in aspen stands. So my study is on quaking aspen, Populus tremuloides, which is the most widely distributed tree species in North America and exists in pure stands and mixed with other hardwood and conifer species. While in some parts of the continent, aspen is referred to as a weed species because of its fast-growing encroaching traits. In the Intermountain West, which is where I am studying, aspen is prized for its aesthetics and recreation benefits, for providing wildlife habitat and forage, and for providing conditions that favor disproportionate understory community biodiversity. Also, in how aspen stands relate to fire, is that aspen has been considered less flammable firebreak forest types, in which crown fires drop to the ground or extinguish, and aspen stands are often considered difficult to burn in prescribed fire situations. So as you can see in this background photo, in a wildfire in the Northwest Territories in Canada, a high intensity crown fire in black spruce stopped when it reached this aspen stand, which protected this community down here. And since the 1970s, aspen stands have actually been proposed as a fuel treatment, but more recently, this idea has really caught on, with interest growing to plant or regenerate aspen in fire-prone communities to reduce fire hazard. So while images of aspen stands stopping fire spread are intriguing, we also know that aspen stands can burn in stand replacing fires, and that even some types of aspen stands may require stand replacing disturbance to successfully regenerate. So we wanted to ask, when does aspen burn and when does it not? Now, I won't be talking about this today, but we are working on a review of the literature, including a survey that we sent to managers to assess our current understanding of fire behavior, severity, frequency, and fuel characteristics in aspen stands. And we have found numerous studies across the distribution of quaking aspen that investigate one of these aspects. But as we synthesize for this review, we're beginning to understand that there is no clear consensus as to whether or not aspen stands are less flammable than conifer stands, or how aspen stands may provide conditions that lessen fire intensity or fire behavior. So overall, we're asking, are aspen stands less flammable than other fuel types? And some studies have approached this question of flammability as the likelihood of burning, but we're specifically measuring flammability as values of fire behavior, such as rate of spread, intensity, and flame lengths. So first, we need to consider under what conditions. For example, does variability in characteristics such as these matter and how much? And then how might aspen stands create conditions that limit these fire behavior characteristics? For example, are there differences in fuel or soil moisture, microclimate, or just the aspen stands have overall less fuel? So for the research that I'm presenting today, I looked at these conditions: understory fuels, overstory composition, and stand structure, and possible explanations: fuel moisture, soil moisture, and fuel amounts. For my research question, I am framing this research along two ecological gradients: overstory composition from pure aspen to mixed aspen conifer, and stand structure from small immature trees to large mature trees. And I'm asking how these stand characteristics correlate with fuel loads and fuel and soil moisture, and if differences in these attributes may reflect differences in modeled fire behavior. In the stands that I studied, we primarily had subalpine fir as the sole conifer species, though a few Douglas fir and Engelmann spruce were also on the landscape. I hypothesized that flammability measured by modeled rate of spread, fire intensity, and flame lengths will increase along both the structure and the composition gradients, with mature stands of mixed aspen and conifer exhibiting higher flammability because of increased fuel loads, particularly fine dead woody fuels, and decreased moisture and crown base height. I also predict that pure mature aspen stands may exhibit high rates of spread because of increased herbaceous and shrub loads under the higher light conditions that are often found underneath aspen canopies, but that an increase in crown base height and higher fuel and soil moisture will decrease modeled intensity and flame lengths. So to begin to answer this question, we collected data at 40 plots at sites in central East Utah in a range of aspen stands. And broadly, we characterize stands as small aspen, large aspen, small conifer, and large aspen, large conifer. to get a full range across those two gradients. In each of these plots, we collected data on overstory and understory trees, as well as the woody, grass, forb, and shrub surface fuels. And to assess fuel and soil moisture, we collected woody and live fuel moisture from early June to late September in each of these 4 stand types in this map. For the woody fuels, we had 3 replicates per stand of these woody fuel stations with a 10-hour, 100-hour, and 1,000-hour sample in each. And these were weighed in the field each week. And then the samples were taken back to the lab and oven dried at the end of the season to calculate percent moisture. We collected live fuels about every 2 weeks in each stand and collected 3 samples from each representative fuel type from the canopy, understory, litter, and soil. So first, to get into some summary statistics of our overstory trees, so the trees greater than 10 centimeters in diameter in this study. Our small and large aspen stands consist of nearly pure aspen, while the 2 types of mixed stands have an increasing proportion of subalpine fir. And as expected, the large aspen, large conifer stands have the lowest height to crown base, and the 2 stands with larger aspen overstories have higher height to crown bases. In terms of density, the 2 stands with a subalpine fir component have much higher trees per hectare than the pure aspen stands, but basal area is similar among all 3 stand types with those larger diameter trees. Now correlating overstory composition of aspen versus conifer with woody fuel loads. So the x-axis in these plots is the percent conifer by basal area of overstory trees. So over here is the 100% aspen stands, and over here is 100% conifer stands. And the y-axis is a fuel load in megagrams per hectare. So with these small diameter woody fuels, the 1 hours and the 10 hours, we see a clear, though not super strong, increasing trend with increasing percent conifer. But when we look at the relationship of the larger size classes of dead woody fuels, there isn't such a clear pattern. So this appears to align with our hypothesis that conifer stands have more of those fine dead fuels, and is intuitive when you think about the distribution of woody size classes on a conifer tree, which has many of those small branches and twigs on a greater proportion of the bole, compared to an aspen tree, which has much fewer of those very small twigs. Now, when we look at the non-woody fuel, the shrubs, forbs, and grasses, we see an opposite trend in which decreasing conifer cover or increasing aspen cover is associated with increasing fuel load. And this is also intuitive when we consider classic pure aspen stands, such as in this picture, with lush understory vegetation biomass. But there's also quite a bit of variability within pure aspen stands. So if we take the grass fuel and the large pure aspen stands, these dark purple points, we measured grass fuel loads from near 0 to over 0.9 megagrams per hectare. So there appears to be evidence that stands with more conifer composition in them have more small diameter dead woody fuel, while stands with more aspen composition have more live herbaceous and shrub fuel. So what about the fuel moisture? What we expect is that the pure aspen stands, the purple lines, will have higher moisture than the stands with subalpine fir, the green lines, throughout the summer. And we had 3 replicates of each woody fuel size in each stand, which is why there are 3 lines for each color in these figures. And I'm not showing the 100-hour fuels, but they also exhibited a similar pattern. So what we find in the dead woody fuels is that there's very little difference in moisture among the stand types. They all track each other pretty well across the summer and are generally within this 10 to 30% moisture range throughout the season. And similarly with the live fuels, while there is difference in percent moisture of the type of fuel, so for example, the conifer needles are consistently lower in moisture than the aspen leaves, and shrub is consistently lower than the grass throughout the season, there appears to be very little difference in moisture among the 4 stand types in canopy fuels, understory fuels, litter, and soil. And in some of these fuels, such as litter, the aspen dominant stands are actually tending to have lower moisture which is something that we need to look into further. So how all of these fuel load data translate into potential fire behavior in terms of rate of spread, fire line intensity, and flame length. I modeled each stand grouping by stand type with a weather scenario of high winds and dry fuels in the R package fire behavior. And as expected, the small aspen stands have the lowest and least variable value for each of these fire behavior characteristics. But unexpectedly, the large aspen, large conifer stands, these dark green box plots, also have pretty low values, while the stands with predominantly aspen in the overstory are actually exhibiting the highest model behavior. So a few summary points of these preliminary findings. First, I find that a high percentage of subalpine fir leads to increased fine dead woody fuel, but less herbaceous or shrub load. Second, and unexpectedly, fire behavior in mixed aspen subalpine fir stands is lower than large aspen dominant stands, though I should note that this modeling exercise was done under one scenario of extreme weather conditions with dry and windy conditions. Also, while we didn't find a difference in fuel moisture between pure aspen and aspen conifer stands, pure aspen stands had a higher proportion of live fuels, the shrubs, forbs, and grasses. And throughout the summer, these live fuels had higher moisture content than the dead woody fuels, which are more characteristic of the conifer dominant stands. But if these live fuels dry out and cure, fire can spread quite rapidly through aspen stands, which we saw in our modeled fire behavior. I should also mention that this summer in this location seemed to be rather wet, particularly every time that we went to collect fuel moisture. So we may need another field season of fuel moisture collection to find a difference among the stands. So the next steps for this project are to incorporate the sapling and seedling density and biomass data, consider other fire behavior characteristics, model fire behavior under other weather conditions, and likely collect more data. So in conclusion, aspen stands may limit fire spread under certain conditions, but we still need to assess how variable those conditions may be and whether in a future climate those conditions still hold up. So as part of our literature review that I mentioned in the beginning, we also sent out a survey to managers last year with expertise in aspen fire encounters. And many respondents expressed that conditions in aspen stands may have changed over the last few decades, in which fire behavior in aspen is quite variable, and the aspen is not so much a fire break as it used to be. Thus, aspen stands may not be the fire breaks that we are hoping for. So with that, I would like to thank my co-authors, the wonderful folks in the Fire Ecology Lab, the field crew this summer, and my funding sources, the Ecology Center here at Utah State, and the Utah Division of Forestry, Fire, and State Lands. Thanks for tuning in, and I'll take any questions or comments that you may have.
Kristin, thank you so much for your presentation. I'm inviting the audience, please go ahead and add any questions you have for Kristin into the Q&A or into the chat. But I see that Jonathan, you have your camera on. Do you have a question for Kristin?
Yeah, actually, I turned my camera on and then you may have answered my question. But great talk, Kristin. And it's fascinating that your results seem like they don't really indicate the same kinds of differences that anecdotally, people have been talking about for a long time. And so I was curious if perhaps that is because, these observations of aspen slowing fires is mostly when we're talking about active crown fires. And so my question was going to be, what about torching indices or crown fire, these transitions from surface to crown fire? It sounds like you're going to be looking at that. So that was going to be my question. I don't know if you have anything you want to say about that or not.
Yeah, great question. I did think about that when I was doing my fire behavior modeling, just to get a whole view of what is going on when a crown fire reaches an aspen stand. So that's definitely something I want to look into further.
Yeah, it seems like canopy fuels are have got to be very different in between contrasting conifers to aspens. So I look forward to seeing what you find. Yeah.
Yeah, thanks. And also, I think seasonality will be a huge factor as well. So I'll have to incorporate that somehow into my modeling, since aspen are hardwood species that, you know, lose their leaves in the summer or in the fall. That'll also probably be a big impact as well.
Kristin, I don't see any other questions coming in yet, but I definitely invite oh, here we have one now. I spoke too soon. You have a question coming in from Tim Curran. Great presentation, Kristin. Is much known about how the flammability of the live fuels of aspen changes seasonally?
That is a great question. I am also curious about Korina's work. She was the first speaker in this session about flammability on a worldwide scale. There are a couple studies that have looked at flammability of like the resins and waxes and things in aspen leaves, and they've done like burning scenarios of aspen litter. So there are a few of those, but I don't know of many more studies that look at like the specific flammability of aspen fuels or aspen trees. But if anybody else knows, would be welcome to that information.
If anyone has any additional thoughts or resources, please feel free to share them in the chat. And Kristin, thank you so much for your presentation. We have just a couple of minutes before our next speaker, but Nathan, you will be coming up right at the top of the hour. So if we want to just transition presentations, we can have you turn on your camera and share your presentation. And Kristin, we'll have you hold on just for a moment in case any other questions come in. We may have folks typing quickly. Oh, it's great, Nathan. Thank you so much. Well, Kristin, it looks like nothing further has come in, so thank you for your presentation today. If we have anything else come in, I'll make sure to let you know so you can answer directly in the Whova app. Thank you so much. And Nathan, you're going to be up next. We have about a minute before your presentation begins. We have a couple of new folks joining the room. Welcome to new folks just joining. We're here talking about our sort of the break that we have going on between sessions. So we have just another minute before Nathan begins his session. Thank you all. And it looks like we have another question that comes in. Kristin, the question's for you. And the question was, would you recommend that communities plant aspen fire breaks, or are you cooling on that idea?
I think I'll have to wait and see for a little bit longer. I don't know. I don't have a good answer to that yet. But we shall see. Maybe in another year after I finish my master's, I'll have a better answer.
Great. Thank you. Tim says that's a good answer. So thank you, Tim. We appreciate it. All right. Well, let's move on with our conversation about bird behavior. Welcome to our new guest joining us, our next speaker, Nathan. I'm going to go ahead and turn it over to you.
Fantastic. Thank you so much. And thanks everyone for being here this afternoon. My name is Nathan Pavlovic, and I'm lead geospatial data scientist at Sonoma Technology, where we work on a variety of wildfire smoke, and air quality challenges. And today I'm really excited to be sharing some work that we've been cranking on here for about 2 years now to look into the opportunities to use satellite data to develop consistent daily and sub-daily maps of wildfire growth over a nearly 2-decade period, and with the opportunity to extend that as we move forward in time. I just want to acknowledge my collaborators here at Sonoma Technology, Crystal McClure, Ximing Wang, Melissa Chavest, and Ningxing Wang. All did a ton of work on this, and I'm really privileged to share the efforts that the team put into this today. Let's see. So today I'm going to cover a few pieces of this work. The first is the motivation. So I think we all know there's a lot of fire activity data sets out there, and so I think the first question on my mind, probably if I were to be listening to this and many others, is, why do we need a new fire database? And so we'll go into that. I'll move on to the method that we've developed as a part of this work and share out the results for our fire history, along with an evaluation of how well these data sources reflect what actually occurs on these fires using independent data sets. And then I'll just end with some thoughts on where we can take this work going forward. So the motivation here is that there are just a number of growing opportunities to to develop models and train models and evaluate models using high-resolution historical fire data sets. And this covers a really broad range of applications, from understanding fire risk before a burn, supporting information needs during burns for needs including asset allocation, air quality monitoring and forecasting, fire growth modeling and fire behavior modeling, and also for retrospective analyses, such as the uses for air quality modeling in health exposure research. And to meet these needs, there's a few characteristics that are really required from a database. These need to be have high spatiotemporal resolution. So we need to know where the fire was burning, not just, so that the fire started on August 15th and ended in September 3rd, and was 100,000 acres, but actually where on each of those days, or even within each of those days, was the fire burning. And that's really critical for understanding the air quality impacts from fires, from understanding the ecological impacts from fires, and for understanding where a fire might go into the future. Another need, and this is one that we haven't seen as much in historical in other data sets that are that exist, including some work that I've been involved in, is spatiotemporal consistency of the data set. So a lot of data sets use information from a variety of sources, including agency reports that vary across state lines, that vary across agencies, and can even vary within a state due to differences in reporting over time or over jurisdictions, or just the quality of the data from one point to another. And so in developing this data set, we were looking for a methodology that would overcome some of the spatial differences or temporal differences in the characteristics of the data reported, because this is really important for developing any sort of statistical modeling or statistical evaluation of models in a data set. And the last requirement that we had in mind in looking at this was a long-term data set, something that could provide years worth of data over broad areas, in this case, California, while providing the characteristics that we've talked about. And I think there's applications for this data set, across a broad range of areas in the fire and smoke research world. The development of this was primarily motivated to support PG&E in the development of a statistically consistent input for their fire potential index to support public safety. And so at each step of the way, we've worked really hard to understand the characteristics of the data set and to validate the results. And so that's what I'll be sharing with you today. in order to meet the needs for a consistent data set over long periods of time, we looked at using primarily a set of satellite data inputs to support the fire growth mapping. And in particular, we used source data from 2 satellites, MODIS Collection 6 active fire data and VIIRS I-band 375 meter active fire data. The first covers 2003 to 2020, and the second time period covers 2012 through 2020. These were the primary source for the data set, but as a part of our processing, we're also able, where available and where possible, to match using spatiotemporal relationships. We also bring in agency records that have been collected, reviewed, and cleaned prior to incorporation. And so we were able to pull data sets from a variety of sources, including the FPA FOD, ICS 209, GeoMac, NIFC, FRAP, and the FireStat database to support the mapping, essentially to provide supporting metadata, so we know what the name of the fire is. We have some independent information about fire size, and we have some independent information about when the burn occurred. So these were all useful in the development of our data set. The overall method that we developed to provide this fire growth map covers 6 key processing steps. The first step is to ingest the input satellite data sets and normalize the fire location, FRP, and quality assurance flags within the input data sets for use in subsequent steps. In step 2, we clean that input data set by removing low confidence fire detection points from locations that are known to produce persistent fire detections, and fire locations in the case of this data set that correspond to agricultural lands, because we were focused on wildland fire activity in this case. Those fire detections are then fed into the third step, which is a clumping step, in which the fire detection points are buffered out to represent burned area and merged together for each instantaneous fire observation from the satellite to create fire perimeters. And so the graphic here shows a schematic of what that might look like at that clump step. At that point, each time step is completely independent from each other time step. And so in the fourth step, we associate those aggregated fire perimeters over time to build up a fire growth history at each time step interval from the observations. And so for MODIS, there's 2 sensors available, one on board the MODIS Aqua satellite and the other coming from the afternoon retrievals on, the morning retrievals on Terra, and the Terra satellite. And so we get 4 observations a day, 1 in the morning, 1 in the afternoon, 1 in the evening, and 1 in the very, very early morning. And so those get merged together over time and associated over time, and then merged with independent agency data. The final step then is to export these from the processing script that we've developed here, and those results are exported to provide geospatial perimeters at each observation time step on a daily basis and a total event basis. And those contain information about the fire growth area, the FRP, the fire radiative power, which is a measure of the total heat emitted by the fire, and the information from agency data, including independent area estimates, fire name, and agency estimated fire location. This plot shows a schematic of how we calculate the fire growth over time. At each time step observation, or for the case of the daily growth, for the aggregated perimeters over a full 24 hours, we calculate the perimeter and then subtract off any areas that were covered by a previous burn perimeter. and the resulting remaining area is used to calculate the overall growth area and location for that time step. This produces some edge cases that are probably worth noting, which are shown on the right here. And these include cases where you have fire actively growing, but it's all within the previous perimeter. And so in these cases, we consider that no fire growth has occurred. Another might be that you have no growth over time because there's no active fire retrieval available for that time step. And the third is similar in that no fire detections occurred. And so, as I said, this process is used to produce both essentially per detect growth information as well as a daily growth product. And these perimeters are merged together at the end of processing to produce an overall fire perimeter estimate. And so using these approaches, we developed two fire activity databases, one based on the VIIRS satellite observations and the other based on the MODIS satellite observations. What you see here on the right are all fire perimeters for those time periods for which the VIIRS and MODIS satellite data were available. And you can see that the burn history across California for this time period is extensive, and we can zoom in onto these individual fires to look at how these fires grew. So one of the first things that we did is to map out an individual fire. In this case, we're looking at the August complex, which is the largest fire in California history and burned in August of last year. And you can see that the perimeters from MODIS, VIIRS, and the independent NIFC fire data set show overall broad agreement, but overall the VIIRS with a higher spatial resolution offers greater spatial detail and slightly better agreement with the NIFC perimeter overall. We can also break these fire perimeters down into their individual time step, sub-daily time step growth perimeters. And that's what we're showing here on these two maps. And this is just, we were pretty excited when we were able to generate this. It's a full fire history on a per detect basis for this fire growth, starting at the points shown in yellow and progressing through red points to the purple points shown on the map. And so here again, you can see that there is broad agreement between MODIS and VIIRS. But when we use the high resolution VIIRS satellite, we really get greater spatial detail in the progression of this fire. And we're really excited about that. Our next step then, having produced the data set, was to understand how well this corresponded with reality. And so we performed evaluations of our results at 4 temporal scales. We started at the broadest scale to look at the agreement between total annual area burned statewide for California compared with independent agency estimates from CAL FIRE. We then compared the event total area burned with the agency reported burned areas from the agency sources shown in the previous table. And then we looked at the event daily growth perimeters and the sub-daily growth area using NIROPS and InstaWeb daily perimeters for select fires. And we really, in these approaches, wanted to understand how reliable these results are and whether they could be used in the modeling applications we had in mind. And so the results show broadly good agreement between these data sets. Here we have the MODIS and VIIRS based estimated total area burned shown on the top 2 bar graphs, and at the bottom, a completely independent data set from CAL FIRE and the annual reported fire growth. And you can see that the temporal trends are very similar across these 3 data sets. And again, on the theme that VIIRS is doing quite well, we end up at just about 4 million acres in 2020 as an example for both the VIIRS fire perimeters and the California agency reported area burned. We next looked at individual fire events to understand how well we were estimating fire area using our satellite-based database. And here again, we see good agreement between our independent data set and from agency reports and our satellite data set. On the top are the results for MODIS compared on the y-axis compared with the agency reports on the x-axis, and in the lower plots we see the VIIRS data set. And in both cases we see an R-squared of 0.95 or better between these two independent data sources. And we follow our slope is pretty good as well. One thing to note here is that the August complex is a pretty extreme outlier. It's the point in the upper right of the scatter plots. And when we remove those, we end up having a best fit line, which is shown in black on the plot, that slightly overestimates fire area for MODIS and falls just below the one-to-one line in red for VIIRS. And so we're really encouraged with the results that we're seeing here on a per fire basis. Two other things to note here are that when we zoom in to look at the fires that are below 10,000 acres, we can see that the high resolution of the VIIRS data really comes in as particularly valuable in improving the agreement, whereas we see a pretty broad spread in these smaller fires between the MODIS data and the independent agency reported area. And then on the right, you can see the distribution of fires that were matched between the satellite observations and the agency reports, and fires that were unmatched in red. And the main takeaway here is just that we do have fires that don't have a match between those two sources, but by and large, these are very small fires where we have a couple of problems. First, these are small and generally quick burning, so we have less chance to observe them using a satellite imagery source. Second, we see a lot of quality issues in the agency reports where the location of the fire is often reported as the point where the firefighter happened to be when they were responding to a fire rather than the actual location of the fire. And so that complicates the merging step between these two data sets. We were also able to evaluate the agreement between our independent data set and the daily growth and the sub-daily growth from agency reports and the satellite data. Again, great agreement between these two. For the independent daily growth, it's a little bit off, but I'll touch on why that is in a moment. If you look at cumulative fire size day by day, we see great agreement between the NIROPS and InstaWeb data and the satellite data. We also look at sub-daily fire area using precision and recall, and the VIIRS data and the MODIS data show really good precision, recall for precision. It's a little bit lower, and that's really driven by the fact that our NIROPS data generally don't cover all of an actively burning fire. And so you can see an example here. The gray boxes show where NIROPS data were collected, and you can see that there's blue and red perimeters that we detect with MODIS and VIIRS that just don't show up in the NIROPS data set. And so when you sort of look outside of those, we're seeing really good agreement between these two sources. So in conclusion, we've developed a database and validated a database that provides sub-daily fire growth data sets. And the agreement between this satellite-only data set and the agency data that are merged in subsequently really shows good agreement between those sources. So we believe that this provides a consistent record of fire activity, and we are really excited and looking for opportunities to collaborate with folks on how this can be used for statistical modeling of fire risk, fire growth, smoke emissions, and other fire-related activities. So thank you very much, and I think we're right up against time, so happy to take questions if there is time, or chat offline. Thank you.
We are indeed up against time, so thank you so much, Nathan, for your presentation. If anyone has questions or is interested in any further information from Nathan, please go ahead and put them in the chat. Nathan, when you have an opportunity post the session, you can go ahead and jump into Whova and answer any remaining questions. Up next, we have Taro. Taro, if you want to go ahead and share your presentation, we can turn the stage over to you.
Hi, good day. Can you all see my PowerPoint okay?
Yep, that looks great. Thank you.
Yeah, I'm Taro Pusina with Spatial Informatics Group as a wildland fire and fuel specialist. I'm also a fire behavior analyst on a federal California interagency incident management team here today presenting Pyrecast as part of the Pyregence Project, which is an open source near-term fire behavior forecasting tool from a fire behavior analyst perspective. And just a quick sidebar, I'll date myself here. I was fortunate to be able to attend, I believe, the first AFE conference back in 1997 in San Diego, and quite a few subsequent AFEs, which were very motivational, inspirational to me as a close to 30-year wildland federal fire responder, a fuels and prescribed fire implementer, and in science-based wildland fire response and suppression. So it's an honor to be able to present today. I was always petrified to present, and I'm still petrified, so I apologize if I stutter. Hats off to AFE and to everyone here in attendance for continuing this excellent program. I'll start with a few PowerPoint slides, and then technology permitting, hope to give a demonstration of the actual software. I need to acknowledge the funding and the brains behind Pyrecast. Pyrecast is currently funded by the California Energy Commission and the National Institute of Standards and Technology. The team, of course, there we go. The team, very quickly, with Spatial Informatics Group, principal being David Saw and Shane Ramzos, heading up the Pyrecast project. Weather analysis by Janice Cohen and her team and folks. The tree mortality and fuel measurements and mapping, Scott Stevens and Brandon Collins from UC Berkeley. A lot of the modeling and the formulas behind what's going on here. Chris Lautenberger with Reax Engineering and Spatial Informatics and other private sector folks. The long-term projection modeling, Leroy Westerling and Matt Herto with UC Merced and University of New Mexico. And then John Battles with UC Berkeley on the science integration and advice. So it really is a collaborative effort between educational institutions, private sector, federal, and even state, and CAL FIRE here in California. Some of the guiding principles behind this project is that it's squarely grounded in science. It's guided by user needs and operational experience, truly collaborative across sectors and research areas. This is open source, free information and data and accessibility to anyone. And the science and technology behind it is available to everyone. There's also technical advisory committee oversight as well. So I'm gonna close my slideshow and try to open my the actual program here. So please bear with me while I do that. Let's see. And can you still see my screen with the Pyrecast program here?
We can, and it looks like a disclaimer window is over top of it.
Okay, good. With that, I'd like to go over some of the assumptions of the program. This is a near-term spread model. Currently, it will model 4 days out from the time that you run it. It's a stochastic or Monte Carlo type of a spread model. And it uses Rothermell's spread model in the background with the assumptions of elliptical fire spread and shape, Van Wagner's transition to crown fire, and Cruz and Alexander's crown fire spread models as well. So these are the current platforms for, I believe, most, if not all, of the current fire spread models out there. Some of the differences with Pyrecast is that it's an ensemble set of inputs, including things like fuel moistures. The weather input stream is gridded from NOAA at 3K resolution. It will demonstrate graphic fire spread, which is very, very useful for me, as we'll see here shortly. And it is open source, available to all. Some of the limitations that I'll point out, well, this is still in beta mode, so please be patient with it if you try it out. We can't upload polygons or shapes or barriers as you can in fire spread probability, like in WFDS. You cannot input previous fire or fuels treatments or history yet. These are things that we'll be working on into the future. And then just some of my personal disclaimers. I'm squarely an operational wildland fire responder for most of my career. I'm not a computer programmer. I'm not a modeler. I'm not super savvy with data management. And this tool really provides an easy, user-friendly way to model fire spread to a whole variety of audiences, including, in my case, incident commanders, operational section chief, division group supervisors, firefighter boots on the ground, decision makers, line officers, the private sector, anyone who's got an interest in where the potential fire could go. It's incredibly visually stimulating, simple to use. And so as a fire behavior analyst, I'm primarily interested in weather, fuels, and topography as they pertain to fire spread, and then relating that information to pertinent parties in a way that's understandable and doesn't gloss people's eyes over. And oftentimes, if I'm just producing numbers to people, flame lengths, rates of spread, chains per hour, things like that, you lose people's interest. So this program allows me to demonstrate some of that. I use this program in concert with Behave, which is sort of the gold standard for modeling fire spread. So when you first boot up pyrecast.org, this is what you're going to get. You're going to get a map of essentially the United States. And you'll notice there are 4 primary tabs up on top. And I'm going to jump right into the active fires tab. One thing I really like about this is it's kind of got the Google Earth style background, and you argue it's kind of year round now. You'll have a list of active fires here on the left that you can toggle on and off that will show up on the map based on their heat signatures, their VIIRS and MODIS heat signatures. The Pyrecast team was kind enough to load up 2 active California fires this summer. Some of you may be familiar with the Dixie fire that burned in Northern California. So when you toggle that incident on, we're going to be going back to July 22nd of this year to where the fire was at that point, the heat signatures that it was showing, and the background around that. So one of the first things that I do is, well, you can change things like the background, you can make it light or dark, but you've got interactive menus and tabs all around. One of the first things I like to do is enable 3D terrain, which allows you to basically look at it from any angle. And then here on the left side, the base map, I like to use the satellite street version because it gives me sort of a better idea of topography, communities, roads, ingress, egress, and an idea of the fuels and vegetation. With with this fire in the background, I will move over to the weather tab, which once you toggle that on, you basically, so this is today, December 3rd, here up in Northern California, near where the Dixie fire was burning. You've got your temperatures, and then you can select any point on the map and basically get from here to 60 hours out what your temperature are going to be. And then primary inputs for fire behavior, of course, besides temperature, are relative humidity, wind speeds, sustained, and gusts, which I think is pretty well known that wind above all other factors is the primary driver of fire spread, and slope, as was mentioned in an earlier presentation, but just incredibly useful wind information, fine dead fuel moisture, another primary input and driver of fire spread as well. I'm not going to go into all of the different weather parameters that you can access, but they're all right here. You can play around with it. Fuels, probably the next most important driver of fire spread. Fine fuels being the typical primary driver. And you've got 4 different options on fuels backgrounds, from land fire to California Forest Observatory, California Fuelscape, California Ecosystem Climate. I will play them off of each other and usually pick the one that's going to be the most active and work backwards from there. So, for example, this particular point on the landscape under land fire shows a timber understory 5 under Scott and Bergen's. California Fuels Forest Observatory is a timber understory 2, and Fuelscape is a TU5, and California Ecosystems is a TU2. So of those, arguably the most active is probably going to be the TU5, and you can use multiple inputs and behave. But typically when I'm on a wildfire incident, I will physically either hike or drive out to the fire to ground truth and validate what's going on here. But in the meantime, oftentimes you need to get a product out quickly. And so this is a quick way to get the fuels. I'm not going to go too much into the risk, other than to say that the risk tab will model millions of hypothetical fires and give you an idea of fire area, fire volume, and potential threat structures that can be threatened. I'm going to move right into the active fires tab and model spread. Well, we still got a little bit of time left on the presentation here. And the way you do that is once you've got the fire toggled on in the upper left here, you come down to this menu down here. I'll put it into local time, and you can model it at the different percentiles. Obviously, the 90th percentile is going to show a more rapid spread. The 10th percentile is going to show the least. I'll usually start in the middle or even up at the high end, the way fires have been acting and behaving the last few years. And what we're finding is that it's coming fairly close to actually showing how fires are spreading. You can model how fast it's spreading. And so I'll go ahead and put it at 0.5 speed and run the animation. And let's just hope it works here. So, and really the interesting thing is that it literally models the spread in front of your eyes. I know there are other programs that can do this. I'm not aware of any other open source programs that allow you to game fires out in this manner. And I think, as many of you know, that this fire was very large and fairly destructive. It pretty much leveled a couple of communities, but I think with that, looks like I'm running up at about 15 minutes. I'll just say that from here, where we're hoping to go with the project is to continue to find stable funding sources for it, to keep it collaborative. We acknowledge its limitations. It can become unstable when there are multiple large complex incidents because of the programs running in the background. It can get bogged down. So we're trying to develop more stability with it. We're also giving certain users advanced tools to use, like the ability to drop a match or ignition. I personally am very proactive with fuels treatments prior to large wildfires, and using it to demonstrate pre and post treatment fire spread and potential to a number of different audience types. Those are some of the things we're looking at into the future. So with that, if there's time, I can try to answer questions. If not, I can get back to you.
Thank you for the great presentation. It does look like we already have a question coming in. Unfortunately, the question is being provided in Spanish, and I don't read Spanish. So I'm wondering, Taro, if you might be able to take a look and see if there might be an opportunity to answer it in Huva after the presentation.
Absolutely.
Great, thank you. Does anyone else have any questions? We have just a couple of moments before our final presentation. If you have any questions, go ahead and enter them right there into the Q&A or the chat.
And unfortunately, this community of Greenville did mostly burn not that long after this date. So
I see we have a number of additional folks who have joined us during your presentation. So thank you for sharing the demo. It looks great on Huva. We do have one of our guests did a translation of the question for us. The question is, didn't know that Pyrocast. Do you have images and information from Brazil or other countries besides the United States? Thank you for interpreting, Henrik.
that's a great question. And initially we were, of course, very Western US centric, and now we're trying to expand across the continental US. And if we can sustain funding and support, we absolutely would like to go worldwide with it. Obviously, there's a lot of data going on in the background, and it takes time and effort. So we're working on it, though.
Great, thank you so much. I don't see any other questions. So as we continue our conversation about fire behavior, we have one final speaker today joining us, Jonathan Coop. You will be up next. If you want to go ahead and share your presentation, we can get you all set up. That looks great. And Tara, we got to thank you from our previous question. So thank you for providing that information. All right, well, it looks like we have a couple of new guests that are joining us for our final presentation. We'll go ahead and get them set up and turn it over to you, Jonathan, if you want to get started.
Yeah, sure. Well, for those of you who are tuning in still here, thanks for sticking around to the almost the end of this meeting. Definitely want to give a shout out to the previous presenters in this session and the conference organizers. If it were up to me, I guess we'd be about to enjoy some cocktails on the beach and talk fire science, but unfortunately, we're still in a virtual reality here. But hopefully we'll be back in that realm soon. So yeah, I'm talking today a little bit about extreme fire spread events, which I'll define shortly. An area burned under recent and future climate in the Western US. Here's some Earth observatory imagery from NASA of the East Troublesome Fire in Colorado, which will feature into this presentation. So we'll talk a little bit about just the distribution of daily fire spread events, relationships between these daily fire spread and annual area burned, climate fire spread relationships, and some future projections and implications. And I want to give a huge shout out to my collaborators on this project, Sean Parks, Camille Stevens-Ruman, Chad Hoffman, and Scott Ritter. And also just note that everything we'll be covering here is currently in a paper in review, so hopefully we'll have something out before too long there. All right. So probably don't need to convince people in this audience that warming and drying conditions are leading to increasing wildfire activity, particularly across the US, but also in many regions of the globe. And that's been pretty well demonstrated at this point. Frequently, that activity is measured in terms of area burned or annual area burned. And there's lots of great climate predictors of that, and also projections suggesting that under future warmer and drier climates, we'll see more area burned. Also, we're starting to see more studies looking at patterns of fire severity, and with increasing annual area burned, we're also seeing increasing area burned severely as well. So trying to flip slides here. But I also want to point out that in addition to increasing area burned, recent years have been characterized by these observations of just exceptional large single day fire runs. And so to highlight a few of those, 2020, of course, presented us with a confluence of ignitions, extreme drought that intersected with rare weather conditions and led to some just really incredible fire behavior. So I'll highlight a few of those from the West Coast here, the August complex in California, which made about a 50,000 hectare, which grew about 50,000 hectares over just a couple days in September. And this was, of course, the gigafire that burned over 1 million acres total when all was said and done. Lion's Head fire in Oregon showed a reported growth of 36,000 hectares between September 8th and 9th. And then the Holiday fire grew to about 42,000 hectares by the end of the second day on September 9th. And of course, those fires were largely associated with unusual east wind events along the crest of the Cascades and the Sierras. But just to exemplify a few of the kinds of massive growth days that we've seen. So yeah, and over down here in the bottom left is just area burned from NIFC, and 2020 is there in red. So yeah. Okay, well, so many of us were just sort of watching in awe as these events unfolded. And I'll just point out that here in Colorado during that time period, that early September timeframe when a lot of this stuff was blowing up on the West Coast, we were getting a really large snowstorm, which we all thought was sort of a season-ending event, but it turned out not to be the case. And we had a fire that blew up in October. And so this is late October. The East Troublesome fire made this unbelievable 35,000 hectare run, basically between 6:30 p.m. and 12:30 a.m. So over a 6-hour period, it was burning about 4 acres per second, and then added an additional 18,000 hectares by mid-afternoon on the 22nd. So basically, this was a fire that achieved, a mega fire size run in less than a single day. And I think to many of us, I was on an earlier meeting today with some fire managers, and this fire has, I would say, really changed our dialogue and our thinking about what the future may hold here, and what sort of, what sort of management interventions we need to be thinking about. Of course, these are fires that just absolutely defy our fire suppression. This fire was sort of the genesis of this study in terms of, I just found myself wondering, like, how crazy was that really? Like, it seemed totally unusual and bizarre and ginormous, but how does that fire really fit into what daily fire spread rates normally look like. What does that distribution of single day fire spread events really look like anyway? And then how important are these kinds of extreme events in aggregate fire effects? So in, for example, annual area burned. So this leads to our methods, which was the development of these day of burning maps using VIIRS and MODIS fire detections for the Western US, for our Western US study area. And this methodology follows Sean Park's 2014 paper. And it was great to have Nathan's presentation earlier because that really paralleled the methods here in terms of basically interpolating fire detections and developing perimeters for each set of detections to develop single day or even sub-daily maps of fire spread. And just a few other notes on this methodology. We developed these detections and then constrained the final fire, constrained our maps to the final fire perimeters from MTBS and NIFC. Excluded small fires for consistency between data sets, so the stuff that's not included in MTBS, and also eliminated fires with less than 10 detections, just because of the increasing uncertainty associated with interpolating really small numbers of detections. Fire detections that occurred between 12 a.m. and 6 a.m. were assigned to the previous day, just because we don't know exactly when those things burn, but generally those detections are associated with area that had burned during that previous day. And so what we ended up with was day of burning maps for 2,391 fires and a total of 21,006 unique fire spread events, which basically we're defining as single day fire spread, which ranged in size from 25 to almost 75,000 hectares. Okay. And so just over there on the right are a couple of images illustrating what these day of burning maps look like. Okay, so I was just interested in, what even is the distribution of daily fire spread? And this is when all is said and done, this is what it looks like. It's basically a log normal distribution, and with a log mean of about 295 hectares and a median of about 260. Because the mean is farther to the right than the median, that means it's also a little bit of a right skewed distribution. We are certainly missing some of those really small spread events over there on the left, but I don't think that is what accounts for that right skew. And I don't think that alone accounts for the right skew of this distribution. Okay, next question. How crazy was that East Troublesome run? Well, it was actually pretty crazy. It was number 8 in our data set of all-time biggest single day fire spread events. And I think we could have probably juiced the numbers a little bit if we wanted, if we'd have changed our definition of day from, say, 12 a.m. from noon until noon. I think we could have had a bigger one there. But anyways, over that essentially 24-hour period, it was number 8 on our list of all-time top fire spread runs. And then the other question we're asking is, how important are these single day fire spread events in aggregate fire effects? So this graph is just overlaying cumulative area burned on the other right side x-axis with daily fire spread. And so that red line represents cumulative area burned, and there's our frequency distribution in the hollow columns. So we're defining extreme events as greater than 1 standard deviation from the log mean. And those events actually, so it's greater than 16% of our of events account for 70% of our area burned. The top 10% of events actually account for 58% of area burned. And this is pretty interesting statistic. Just the top 1% of daily single day fire spread events accounts for 20% of total area burned. So to answer the question, it seems like these events are indeed pretty important in, for example, determining annual area burned, among other things. Okay, I was also interested in this question: how do patterns of daily fire spread shape annual area burned? What makes a big fire year? Here's 3 different non-mutually exclusive hypotheses. I'm illustrating hypothesized frequency distribution for a normal fire year and a big fire year here. So maybe big fire years are just characterized by more events, right? So if we see more events, we just see that whole curve getting shifted up, and that's what maybe that's what makes a big fire year. Another hypothesis is that the size of individual events is greater. So maybe a big fire year has the same number of events, they're just larger, and the whole thing shifts a little bit to the right. And finally, another hypothesis might be that there's just more skew. So just more large events in a big fire year, and you end up with something like that. It's just a little more right skewed, but you end up with a few more events way out there on the tail. And these are important in, as I said, accounting for a giant portion of the area burned, or some fraction of the area burned. And this turns out to be, when you make a little linear model, all of these are significant, but number of events is the biggest contributor. Mean event size accounting for only about 30% of the of variation in total annual area burned, and skewness about 3%. And so this is just illustrating 2020 compared to 2002 to 2019 in terms of total area burned or number of events and daily fire spread. So in 2020, of course, much dramatically more area burned than the mean of that time frame. So more events, larger events, and also more large events. Okay, do extreme events relate to climate? And of course, I'll just offer the caveat right away. Yeah, we know that these things are associated with weather and extreme, wind and things like that. But also we would expect that a number of climate predictors like climate moisture deficit, Tmax, vapor pressure deficit would be associated with greater rates of fire spread, because these are things that, either predispose fuels to greater rates of spread. They are associated with atmospheric conditions that are more conducive to spread, less humidity, warmer temperatures. And these are also factors that increase the fire season, and thus the likelihood of overlap between any given fire, the likelihood that a fire during that season overlaps with extreme weather events like what occurred in September of 2020. And I also want to note that we developed sort of a metric that we're just referring to as aridity for the sake of anything better, which is the average z-score of deficit, Tmax, and VPD for this reference period of 1986 to 2015. All of these climate data are from Terra Climate, by the way. We summarize these climate metrics for 3-month fire season climate periods, and basically developed, looked at correlations, but also developed a model predicting total count of extreme fire spreads based on these different metrics, including this synthetic metric that we're referring to here as aridity. And so over here on the right, we broke this area up into these 4 forested regions, and you can see approximate relationships between our aridity metric and number of extreme fire spread events. So these are events larger than that. Top 16%, they're larger than 1,100 hectares, and very strong correlations. I'll highlight, here's a little box highlighted in red. Across the Western US as a whole, aridity and these other metrics are all strongly associated with number of extreme fire spread events. And that's also the case with our generalized linear model, which we developed to do some projections of how these numbers might look in the future, which I'll get to next. So to answer my question, do extreme fire spread events relate to climate? Yes. Okay. What are we seeing under a future climate scenario? This is a +2 degrees C relative to pre-industrial scenario as developed by Terra Climate. So the nice thing about this scenario is it allows you to look at year-to-year variation over a future climate period compared to that reference period. And so we're not only able to model means in the future, but also get some of that variation and also look at extremes. And so if you look at the graph on the top left here, you'll see the reference versus the +2 C projected climate in terms of these climate variables. climate moisture deficit, Tmax, VPD, and aridity. And the red dot there represents 2020. The blue box plot is reference, yellow, orange is future. And you can see that for many of these variables, including our synthetic aridity variable over there on the far right, 2020 represents sort of almost a norm of future climate predictor variables. So how did this, when we ran our generalized linear model and basically predicted extreme fire events under the future climate, that's the graph in the lower left, we see that the number of extreme events is dramatically higher under that 2 degrees C future climate scenario. And there's the red dot is 2020 again for reference. So we go from 2020 essentially being an outlier in terms of lots of these extreme events to basically representing the beginning of the 4th quartile. So essentially 1 out of every 4 years would be equally as bad, if not worse, than 2020 as far as numbers of these extreme events goes. So just to give you some numbers on that, reference period means 129 extreme spread events per year, ranging from 32 to 302. Predicted mean was 343 under that +2 scenario, ranging from 81 to 815. So again, the extremes are likely to be dramatically more extreme than what we've seen so far. We also developed some similar models given the relationships between extreme fire spread events and area burned. We also developed some similar models just for area burned, which also suggests we would see essentially more than a doubling of area burned under this future climate scenario. Okay, so I'm running a little bit low on time here. I just got one more slide. So just the take home messages here are based on these approaches. Anyways, we can expect increasing numbers of extreme single day fire spread events and growing annual area burned. And also want to emphasize that future extremes are likely to exceed anything that we have witnessed yet. And the graph on the lower left is something I just like to show to keep our spirits down. Just a reminder that we're still down there as far as the extent of climate change that we are exposing ourselves to. And what the future holds is of course uncertain, but many projections suggest we will quickly exceed that +2 degrees C relative to reference period. So that is maybe a fairly conservative estimate of future changes. Okay, a couple important caveats here. These models, of course, assume that future climate fire relationships are similar to those today. And there may be ways that changing fire management or feedbacks could alter those relationships. And then caveat number 2 is the climate models account for only about 40% of the annual variation in number of extreme events. So I would say that's still calls for accelerated climate mitigation efforts, but also tells us there's other variants that we can account for. Probably a lot of that's associated with fire weather. And there's some opportunities for future research there, but perhaps also vegetation and fuels and the things we can actually do something about if we're unable to reduce our exposure to climate change. So big question is, what is our capacity to influence these relationships and future outcomes via management interventions? And I think certainly we know that we have a long ways to go in terms of community safety and reducing economic exposure and lives lost. But as far as ecosystems go, I think there's a lot of questions there about what, if anything, we can do to reduce fire spread under these extreme events where fire suppression is basically not an option whatsoever. So yeah, if there's any time left, I'd be happy to address any questions you might have. Thanks for tuning in, and feel free to shoot me an email if you're interested in further discussions. Nathan, I really thought maybe there's some opportunities to compare methods with what you've got cooking over there based on your earlier talk. So yeah.
And Jonathan, in our last 30 seconds, I do have one question from Garrett that has come in. Garrett says, very cool study. If 2020 far exceeds the reference climate data and matches the future norm, would you also anticipate extreme outliers in the future?
Absolutely. And one thing we found was our models, as good as they were, which, you know, they're decent for ecological or those kinds of models. I mean, we were still unable to, they underestimated the extremity of 2020. So our predictions for 2020 using our model basically came in under what we actually saw. So, you know, not every year is going to be that crazy or as, you know, nearly that crazy, but we can certainly anticipate changes in the mean and extremes that are perhaps, you know, outside of our models, certainly.
Great, thank you, Jonathan. Well, I want to thank all of our presenters today for great research and information on fire behavior. I also want to make sure everyone knows that this was recorded. It will be available in Whova for you to come back to. And our closing session is just beginning. So we encourage you to head over to our closing plenary session. The session will feature AFE special award announcements and our keynote speaker, Paulo Fernandez and Lenya Quinn-Davidson. So to choose to get over there, you'll want to use the agenda tab to the left of your screen, click sessions and click the main session title to join. Thanks again to all of our speakers. Enjoy the rest of your day.